Hello, ma'am. Good day. This is Lenard Facun from B73, and I will be reporting the stress strain behavior. So, stress strain diagrams. It is a tool for understanding material behavior under load. A stress strain diagram helps engineers to select the right materials for specific loading conditions. Or it is a graph that represents how a part behaves under an increasing load and used by engineers when selecting materials for specific designs. So next, so a stress strain diagram generally contains three regions. We have the elastic region, plastic region, and rupture. So what is specifically is elastic region? So this portion is generally represented as a linear relationship between stress and strain. If the load is released, the specimen will return to its original dimension. So for plastic region, in this portion of the specimen begins to yield. The maximum strength of the specimen occurs in this zone. The specimen endures some permanent deformation that remains after the load is released. So for the rupture, the point at which a specimen breaks into part. So next slide. And stress strain diagram are generated experimentally through the performance of controlled tensile tests using fabricated test specimens. So the applied load and displacement are monitored during the test and are used to calculate stress strain respectively. Next, the stress strain diagram differs from various materials. Engineering materials are classified as either ductile or brittle materials. Ductile materials is one having relatively large tensile strain up to the point of rupture like structural steel and aluminum. Whereas brittle materials has a relatively small strain up to the point of rupture like cast iron and concrete. For ductility is the ability of materials to deform under tensile load. High percentage elongation and percent reduction of area indicate ductility. So for the brittleness materials failure with later deformations. Low percent elongation and percent reduction of area indicate brittleness. Next, so stress and strain. So this is direct stress. Direct stress, when a force is applied to an elastic body, the body deforms. The way in which the body deforms depend upon the type of force is applied to it. So in this diagram, the first diagram, compression force makes the body shorter. So in this kind of direct stress, compression, the force or the material when applying load, it will become shorter. It is called compression. While in direct stress, that is tensile force, makes the body longer. The difference between them, the compression makes the materials shorter, but in the tensile load, the materials can be elongated or more longer than the compression. So next, so tensile and compressive forces are called direct forces. Stress is the force per unit upon area, which is acts. So stress is equal to force over area. So the unit is Pascal or Newton per meter square. Then the symbol for stress is sigma. It will be written as sigma is equal to F over A. So most of the engineer fields use kilopascal, megapascal, and gigapascal. Next. So direct strain. In each case, a force or F produces a deformation of X. In engineering, we usually change this force into stress and deformation into strain, and we define this as follows. Strain is the deformation per unit of the original length. So strain E is equal to X over L. The symbol E is called epsilon. So for the strain, it is called epsilon as represented by E. So strain has no units since it is ratio of length to length. Most of engineering materials do not stretch very much before they become damages. So strain values are very small figures. It is quite normal to change small numbers into exponent for 10 raised to 6 as 10 raised to negative 6 or microstrain. Next. So modulus of elasticity. Elastic materials are always spring back into shape when released. They also obey the Hooke's law. So this is the law of spring, which states that the formation is directly proportional to the force F of x is equal to stiffness. Then the unit is kilonewton per meter. So the stiffness is different for the different materials and different sizes of the materials. We may eliminate the size by using stress and strain instead of force and deformation. If F and X is referred to direct stress and strain, then F is equal to sigma and times area. So and X is equal to epsilon times length. Hence, F over X is equal to sigma times area all over epsilon times L. And FL is equal to FL over AX is equal to sigma over epsilon. So next, this the stiffness is now in terms of stress and strain only, and this constant is called the modulus of elasticity or E. This is the modulus of elasticity is represented by big letter E, where it is equal to F times L over AX is equal to sigma all over epsilon. The graph of stress against strain will be straight line with the gradient of E. The units of E or the modulus of elasticity are the same as the unit of stress. So ultimate is tensile stress. If material is stretched until it breaks, the tensile stress has to reach the absolute limit, and this stress level is called ultimate tensile stress. Next. So this is the stress strain diagram as represented later. We have the ultimate stress, yield stress, proportional limit, in the left side. Then in the bottom side, we have the linear region, perfect plasticity or yielding, strain hardening, and necking. And for the top is the fracture. So this is the whole stress strain diagram for materials. Next. So stress strain diagram. Elastic behavior. The curve is a straight line throughout most of the region. Stress is proportional with the strain. Material to be linearly elastic, proportional limit, the upper limit to linear line. The material is to respond elastically. The curve tend to bend and flatten out. So the elastic limit, upon reaching this point, if load is removed, the specimen is still returned to its original shape. Next. So yielding. A slight increase in stress above the elastic limit will result in breakdown of the material and cause it to deform permanently. This behavior is called yielding. The stress that cause is equal to yield stress at yield point. So plastic deformation, once yield point is reached, the specimen will elongate or strain without any increase in load. Materials in this state are perfectly plastic, and this is called the yielding. Next. So we have the strain hardening. When yielding has ended, further load applied resulting in a curve that rises continuously, become flat when reach ultimate stress. The rise in curve is equal to strain hardening, while specimen elongating its cross-sectional will decrease. The decrease is fairly uniform, and that is strain hardening. While in necking, at the ultimate stress, the cross-sectional area begins its localized region of specimen. It is caused by slip planes formed within material, actual strain produced by shear strain. As a result, neck tend to form. A smaller area can only carry lesser load. Hence, curve downward, specimen break at fracture. stress, and that is necking. Next, so we have the shear stress. Shear force is a force applied sideways on the material, transversely loaded. So we have three different shear stress. We have uh, force applying in a material in sideways when a pair of shears cut in a material. So the second one is when a material is punched, and next when a beam has a transverse load. So these are the different shear stress representing by the images we have in here in the PowerPoint. Next. So shear stress is the force per unit area carrying the load. This means the cross-sectional area of the material being cut, the beam and pin. So the shear stress presented by T is equal to F over A. And the symbol is called tau. So shear stress is represented by symbol T, which is called tau. Then the sign convention for shear force and stress is based on how it shears the materials as shown below. So the shears that materials we have the positive shear and the negative shear. So next, so shear strain. The force causes the material to deform as shown. The shear strain is defined as the ratio of the distance deformed to the length, which is x over L. Since this is a very small angle, why we can say that shear strain y is equal to x over L. The symbol called gamma. So the symbol for shear strain is gamma. Gamma is equal to x over L. So this is the image for the example of shear strain. Next, so modulus of rigidity. If we conduct experiment and measure x for various values of f, we would find that if the material is elastic, it behaves like spring and so long as we do not damage the material by using two big forces. The graph of f and x is a straight line as shown. So the gradient of the graph is constant, so f over x is equal to constant. And this is the spring stiffness of the block in Newton meter. So if we divide the force by area and x by the height, the relationship is still constant and we get next. So here is the formula. If we divide f and area and x by the height or the L, the relationship is still constant even, and we will get the f is equal to area all over x all over L is equal to f over a times L over x is equal to f times L over ax. Is they are all constant, where f over a is equal to tau or the symbol for shear strain. Then gamma is equal to x over L. Then f over a times L over x is equal to f times L over ax is equal to tau over gamma, which is also constant. So this constant will have a special value for each elastic material and it's called modulus of rigidity or G. So next, so ultimate shear stress. If a material is sheared beyond a certain limit and it becomes permanently distorted and does not spring all the way back to its original shape, the elastic limit has been exceeded. If the material is stressed to the limit so it parts into two, the ultimate limit has been reached. The ultimate shear stress has symbol T, which is tau, and it is values to calculate the force needed by shears and punches. So this is ultimate shear stress. Next, so we have the double shear. Double shear considered a pin joint with the support on both ends as shown. This is called clevis and clevis pin. By balance of force, the force in the two supports is F over 2 each. The area sheared is twice the cross section of the pin. So it takes twice as much for a break the pin as for the cases of single shear. Double shear arrangement doubles the maximum force allowed in the pin. So this is double shear image. We have the clevis and the clevis fin. Next, load and stress limit. So design consideration. For the load and stress limit, the design consideration will help engineers with their important tasks in designing structural or machine that is safe and economically perform for specified function. So determination of ultimate strength. An important element to be considered by the designer is how the material that has been selected will behave under load. This is determined by performing specific tests. Example is tensile tests, or the ultimate force is equal to the largest force by the applied for the specimen is reached, and the specimen either breaks or begins the carryless load. So ultimate normal stress ultimate is equal to ultimate force all over area. So this is the formula for ultimate normal stress is equal to ultimate force all over area. So next, so allowable load or stress. Max load that structural member or machine component will be allowed to carry under normal conditions of utilization is considerably smaller in the ultimate load. This smaller load is equal to allowable load all over working load, all over design load. Only a fraction of ultimate load capacity of the member is utilized when allowable load is applied. The remaining portion of the load carrying capacity of the member is kept in reserve to assure its safe performance. So the ratio of ultimate load or allowable load is used to define factor of safety. So factor of safety is equal to ultimate load all over allowable load, or factor of safety is equal to ultimate stress all over allowable stress. So this is the formula for factor of safety. We have the ultimate load all over allowable load, or we have also considered the formula ultimate stress all over allowable stress. Next, so selection of Fs. Variation that may occur in the properties of the member under considerations. The number of loading that may be expected during the life of the structural machine. Then the type of loading that are planned for in the design or that may occur in the future. The type of failure that may occur and the uncertainty due to the methods of analysis. Six, deterioration that may occur in the future because of poor maintenance, because of unpreventable natural causes. And last, the importance of a given member to the integrity of the whole structure. So this is the selection of FS. Next. So we have the actual force and deflection of body. So deformation of members under axial loading. If the resulting axial stress does not exceed the proportional limit of the material, Hooke's law may be applied where uh, when the deformation can be written as sigma is equal to FL over AE. So this is the formula for axial or and deflection of body. You will use the Hooke's law. Next. So these are the sample problem for stress strain behavior. So I will read the question. A nylon string has a diameter of 2 millimeters pulled by a force of 100 Newton. So determine the stress. So we have the given of 100 Newton, which is the force. The diameter of 2 millimeter will be converted to meters. It is equal to 0.002 meters. And the radius is equal to 1 millimeter or 0.01 meter. So we will find the stress. For the solution, area is equal to pi r square, where pi is equal to 3.14 and the radius is 0.001 meter square. So the area is equal to 0.000000314 meter square. Then area is equal to 3.14 times 10 raised to 6 meter square. So the stress will be 31.5 times 10 raised to 5 Newton meter square. square. So the simple uh, simple formula for this is stress is equal to force over area. So stress is equal to 100 Newton all over 3.14 times 10 raised to negative 6 meters square. So the total stress is equal to 31.5 times 10 raised to 6 Newton meter square. So this is the stress in the nylon string diameter that is pulled by a force of 100 Newton. Next. So second problem, a cord has original length of 100 centimeter is pulled by a force. The change of the length of the cord is 2 millimeter. So determine the strain. So we have the given of original length is equal to 100 centimeter, which is equal to 1 meter. The change in length or delta L is equal to 2 millimeter, which is converted to meter. It is equal to 0.002 meters. So we have the original and the change in length. We will define or determine the strain, value of strain. So the formula for strain is equal to the change in length or delta L all over original length. So our formula is equal to delta L over L, which is the change in length is equal to 0.002 meters, and the original length is 1 meter. So for the value of strain, it is equal to 0.0022, and that's all. Strain has no unit. Okay, so the final answer will be strain is equal to 0.002. Next, so here a string 4 millimeter in diameter has original length of 2 meters. The string is pulled by a force of 200 Newton. If the final length of the spring is 2.02 meter, determine the stress, the strain, and Young modulus elasticity. So we have the given of diameter. It is equal to 4 meters or converted to meters, 0.04 meters. The radius is 2 millimeters or 0.002 meters. The area is equal to pi r square. Then second area is the area for this is 0.00001256 meter square or 12.56 times 10 raised to negative 5 meter square. So we have the value of force 200 Newton. The original length is 2 meters and the change in length or delta L is equal to 0.2 meters. So we have to find the stress, the strain, and Young modulus elasticity. So for the stress, we have the given formula is equal to stress over force over area. So the given force is equal to 200 Newton all over 12.56 times 10 raised to negative 6 meter square. So by dividing these two values, we have the answer of 15.92 times 10 raised to times 10 raised to 6 Newton meter square. So for the strain, so we will just get the given delta L all over original length, which is equal to the delta L is equal to 0.02 meters and the original length is equal to 2 meters. So the strain is 0.01. So that is for strain. Then last, the Young modulus. So we have the value of stress and the strain. So where the Young modulus is equal to stress over strain. The value for this is for stress, we have the value of 15.92 times 10 raised to 6 Newton meter square, all over 0.01. So the Young modulus is equal to 1.6 times 10 raised to 5 Newton meter square. So that is the value for Young modulus. We have for the stress is equal to 15.92 times 10 raised to 6 Newton meter square. The strain is equal to 0.01. And by dividing these two, the stress and the strain, we will get the Young modulus, which is 1.6 times 10 raised to 5 Newton meter square. So these are the three sample problems for stress strain behavior. So that's all for today. Thank you for listening. God bless everyone.